Welcome back, those of you that decided to come back. I noticed a couple of people, maybe I scared them away or something. I hope not. Hopefully everybody has a syllabus. This is day 2. I didn't quite do my job yesterday, so I'll try to clean up what I didn't get to yesterday. We'll finish Chapter 1, Section 1, and hopefully complete today 1.2. And once again, I'm hoping that most of this is review. I'll try to point out some areas of the book where you could dig in a little further if you're feeling like it's not review for you as we go through this. So we finished yesterday talking about domains, and I think our last problem was this problem. If it wasn't this, it was very close to this. And we talked about division by zero, and I said I had a lot more to talk about with regard to division by zero. We decided that the domain here was all reals as long as x was not, what, 2, negative 2, right? I think that's where we left off. But I want to address the topic of division by zero just a little bit longer. So we know in division that if we have, let's say, 8 divided by 4, that's 2. And we can check that by taking our quotient times our divisor, and we're back to the dividend, right? So we ought to be able to take 2 times 4, and we're back to 8. Everybody all right with that? So let's try some zeros in there. Well, let's try a 0 in the top. 0 divided by 4 is 0. And does that check? Can we take our quotient times our divisor? And are we back to the dividend? We are, right? So that makes sense. Now, what's the problem with 4 divided by 0? We don't like it, and we've always heard and seen in math that we don't like it. And the reason we don't like it, let's say it's some answer alpha, we would be saying then that alpha times 0 is going to be something that's non-zero, which therein lies the reason why we don't like it. Division by 0, no answer, right? No solution. There is no alpha that we can plug in here, and the problem is we'd have to multiply it by 0. We know what that does to everything. That makes the product 0. Now, let's consider this, because we're going to have to deal with this in this course. 0 divided by 0. That's a different animal. That's a different animal, because I think today, it's a special today, it's a blue light special, that today that answer is 17. Does that check? Yeah, it does, doesn't it? Because 17 times 0 is, in fact, 0. But because that's a blue light special, it doesn't really last long. They have the blue light there, and then they move it to another part of the store. And then the answer becomes 47. Okay, does that check? Yeah, unfortunately, that does too. Because we could go 47 times 0. Is that 0? Yes, it is. So the problem with division by 0, some number divided by 0, is there's not an answer. The problem with 0 divided by 0 is there are how many answers? An infinite amount. So later in this course, and once again in the sequel to this course, 241, you will examine what are called indeterminate forms. And this is one of them, 0 over 0. We don't know what it is. It could be a whole bunch of different things. I could give you a problem right now where 0 over 0 is 3. I could give you a problem where 0 over 0 is 11. And they both would be pretty simple problems. And 0 over 0 is, it varies from one problem to another. So division by 0 is an issue, but so is 0 divided by 0 is an issue that we're going to have to contend with in this course. Next thing we need to look at are, I'm sure one of your favorites, piecewise functions. So we want to look at a function that is, I don't know, let's say it's linear for a while. And let's say it's quadratic for the rest of it. So we've got this function that hopefully is a function. We'll find out when we get a picture of it. That is different. It's linear for a while, and then it changes for some reason, and then it becomes quadratic. So we've got part of a line and part of a parabola. The first line says that the y values can be found by doubling the x value and subtracting 1. Now, what x values can I plug in? What's the domain for this particular piecewise function? I can't use all x's, but I have to use x's less than or equal to 2. So let's put in 2. That's valid. And 1 and 0. And it's linear. That's probably enough, right? But I can't put in a value larger than 2, according to the definition or description of this function. So when x is 2 in this top line, what do we get? 3. When x is 1, 1. That's really enough, but let's get one more. When x is 0, negative 1. Okay, the other line says that the y values are now x squared plus 1. What kind of x's can I put in here? Greater than 2. So do I start with 3?
Yeah.
Actually 2.000001, right? As close as I want to get to 2. Here's how close I want to get to 2. I want to plug in 2. But I'm going to put a little reminder to myself that I'm going to delete this point. I'm going to come right up next to that point, but I'm not going to include that point in the second part. Now you can choose to put in 2.00001. I'd rather not do that and then square it and add 1 to it. Let's just put in kind of the point that we almost get in this piece but don't quite have in our set. If x could be 2, what would be the corresponding y? 5. And now we can use values larger than 2. Let's put in 3. We know what this shape is. We know it's a piece of a parabola. If x could be 3, which it can be, what's the corresponding y? 10. And so on. So let's see if we can get a picture of this thing. So 2, 3 is included. Let's go backward with the linear piece. 1, 1 is included, and 0, negative 1 is included. And we can continue in that linear pattern, right? For all values 2 or less. Now for this piece, I want to know what's going on here near 2. Unfortunately, x can't be 2 in this second piece. So if x could be 2, y would be 5, not included, and then we go from 3 up to 10, and we know that's part of a parabola. So is it a function? It is a function. It's close to not being a function at the x value 2, but one of those points is included, the other one is excluded, so it is in fact a function. And you can put together a variety of piecewise functions. There's a great one in your book on page 15. I guess we'll have to upgrade it a little bit based on what just happened with the price of a first-class stamp going from 34 to 37 cents. But let's upgrade it just a tad. I'm reading on page 15, the second paragraph down. It's problem C, if you want to follow along. The cost of a stamp is 37 cents for up to 1 ounce, plus 22 cents for each additional ounce up to 11 ounces. Is that a piecewise function? Sure is. And if you want to take a look at other examples, I think I asked you to look at a taxi cab problem at the end of the section. That's also a how you're billed for a taxi fare is a piecewise function. If you go over, what is it, 1/8 of a mile, automatically you pay the next higher price, and that one goes, and then automatically it jumps up. So let's see what this is. So anywhere from larger than 0 up to and including 1, we're now paying 37 cents. And if that statement is correct, plus 22 cents for each additional ounce up to 11 ounces, if we have something that is anywhere larger than 1 up to and including 2, what do we pay for that stamp? First class postage. $37 plus 22, right? 22 cents for each additional ounce. So where are we? 59?
59.
And then we keep adding 22 cents to what we pay for anything in that range. Larger than 2, less than or equal to 3 ounces. So 22 cents added to that is what?
81.
81? And this proceeds in this fashion. So what's the picture look like? That's a piecewise function. So if we look at cost here, and the weight over here, 0 to 1, larger than 0, so I guess we need a, what? Open circle here. And then we're going to pay 37 cents for everything up to and including 1. Does that work? Then what happens when we get just a little bit above 1 ounce? Jumps up, right? Jumps up 22 cents. So we've got this jump type of discontinuity. So if this is 0.37, now we're going to jump up here to 0.59 and stay at that level. And so on, right? So we get this step function, this kind of piecewise function. It's different descriptions or definitions of the second elements based on the nature of the first element. So a lot of the things that we see and deal with on a daily basis, in fact, are piecewise functions. Okay, let's take a look at another, actually technically it's another piecewise function, is an absolute value function. The reason it's a piecewise function is because the absolute value of x is defined differently based on the nature of the x value that you plug in. So if x is 0 or larger, isn't the absolute value of that number itself, right? And suppose x is less than 0, how do we get its absolute value? Pretty simple. Change it to a positive. So what can we do to a negative to change it to a positive? Negate it, right? So if we start with a value that is itself negative, let's negate it to make it positive. And there is a piecewise description of absolute value. And we all know what absolute value looks like. And we can have different types of absolute value functions, but the basic absolute value function looks like that. So this really is a line. That's the line y equals x. And that's another line. What line is that? Y equals negative x. So it is, in fact, two separate lines graphed in the plane. And let's segue now into lines. I'm sorry, I am going to go kind of quickly today, but I'm hoping that this is review for you. Let me just set those aside till we need them. If I gave you a point, let's say 3, 5, and a slope negative 2, could you come up with the equation of that line? Okay, do that. And let's check it. Take about 15 seconds. And let's see what everybody gets. Now, you say, well, that's not a calculus problem. Yes, it is. You'll be surprised that we'll be finding equations of lines. We'll figure out the slope at a certain point, use that point, figure out the equation of that line. Does that look like a familiar animal there? Where the y sub 1 is the known y value, excuse me, the x sub 1 is the known x value, m is the slope. Now, your question to me might be, what form should we leave our answer here? It kind of depends on how they want it most of the time. We should be prepared to put it in this form. Kind of a standard form. We should also be prepared from time to time to put it in that form. What is that? What do we typically call that? Slope intercept, right? That's the slope, and that is the y-intercept. So we should be prepared to go either way. What do we have over here? Negative 2x. And then we've got what? Plus 6, right? And if we bring this 5 over here, we'll have to add 5 to both sides. So what? Plus 11? Is that okay? Slope of negative 2. How do you give something a slope of negative 2? If you're drawing that line. Down 2 and left 1? Down 2 and right 1. Okay? Because we want the net effect of the rise and run to be negative. So one's got to be positive, one's got to be negative. If they're both negative, then that's really positive, right? Negative over negative is, in essence, positive. So just one of them we want to be negative. And let's take a look at symmetry. So if we want a function to be even, or if we want to classify a function as even, then that will be true about that function. The f of negative x will be the same as the f of x. Now, an even function has symmetry with respect to the y-axis. So there's a natural symmetry or balance on either side of the y-axis. So if we plug in a and get b, and we plug in negative a and we also get b, that's the thing we're talking about, right? That way the f of negative a is the same as the f of a. So you're handed a function. Let's say y equals, or f of x equals x squared minus x. Is that even? Yes, part of it's even. Is the whole thing even? No. Well, what's the f of x? It's x squared minus x. What's the f of negative x? That's negative x squared minus negative x. Negative x squared is the same as x squared. What's minus a negative x? Isn't that plus x? So is the f of x the same as the f of negative x? No, not even, right? Now, if we had just had x squared or x to the fourth or something like that, we'd be in business, right? Because it doesn't matter whether you put in a positive or a negative, it's the same output. But the problem is we've got minus x, and that keeps this from being an even function. Okay? Second part to this. An odd function. A function is odd is when we can put in the f of negative x and we get the negative of the f of x. So let's try this one. X cubed minus x. What do you think? Think that's odd? All the exponents are odd, right? It'd be nice if all the exponents are odd and we could classify this thing as odd. So there's the f of x. So what's the negative of the f of x? Well, let's just negate this. And then what's the f of negative x? Because there's the negative of the f of x. We need to know that. What's the f of negative x? Negative x cubed minus negative x. Everywhere there's an x, I now replace it with a negative x. That's the f of negative x. And what do we get out of this? So is the f of negative x the same thing as the negative of the f of x?
Yes.
It is. Mm-hmm. There's the negative of the f of x. There's the f of negative x. Those two are equal. What type of symmetry does an odd function possess? With respect to the origin. Okay. Symmetry with respect to the origin. So what happened to symmetry with respect to the x-axis? Why don't we talk about that? That's not a function. That's exactly right. If it had symmetry with respect to the x-axis, it wouldn't be a function. So if it is a function, it can only possess one or the other of these, right? Or potentially both. So what would that look like? If when we put in A, it gives us B, what happens when we put in negative A? If we know it's going to be odd, we know it's going to have symmetry with respect to the origin, it'd be negative B. So we've got that balance on either side of the origin. When you take 2 points that are each other's symmetric image, connect them with a line segment, the origin should bisect that line segment, right? If we've got symmetry with respect to the origin. Okay, the only other thing that's mentioned real briefly, and we'll spend a lot of time with this in this course, is increasing and decreasing. I think we all know what a function is as it increases, that as the x values increase, so do the y values. And if it's decreasing, as the x values increase, the y values themselves are falling. And we'll talk about that with respect to a lot of the calculus that we do in this course. All right, well, let's jump on to section 2. Section 2, you can find these guys, talks about this situation. Initially, mathematical models, and kind of on a baseline sense, we are going to try to use mathematics. Boy, did you hear that crack? Man, I guess I'm getting a little older than I realize here. Hopefully you don't pick that up on the sound. Talk about using mathematics to model real-world phenomena And this is kind of the cycle that we go through. So we look at this real world simulation or this real world situation, and we want to formulate all the data and everything surrounding this that we can. If we know it's linear, it's behaved linearly in the past, we know what kind of model to use. If we know it's exponential, we know it's logarithmic. Those are helpful things. If we have a table, all these things are going to help us to develop a mathematical model. Maybe it's a exponential growth model. Maybe it's a decay model. And then we're going to take this data that we have and we're going to try to fit the model that we think is going to work to the data that we actually have or we've obtained ourselves. And we get our conclusions here. Now, what do we want to use that for? Well, we maybe want to use that to make a prediction. We maybe want to take a decay model. Maybe we've made a spill in a lake of a pesticide, and we want to see if it's got fresh water coming into the lake, how long will the fresh water have to come into the lake to reduce the level of pesticide to a level where it's safe to swim or fish. So we would want to then make a prediction using our model, and then as the clock ticks and we actually, fresh water does come in for 39 hours, then we can actually see if our prediction was valid. So that's kind of the cycle, and if it doesn't work, then we might want to adjust our model and kind of go through the whole process again. Now, there's a whole bunch of different types of models that you have encountered already, I hope. Linear models, we've already talked about them today, and we're just going to touch briefly in the time that remains today on each of these models. Some we want to spend a little more time than others, but I'm hoping that as you look at this list that you've dealt with them. Maybe not extensively in all cases, but you've at least dealt with these types of functions. So linear models, you'd be surprised. I don't know. Let's just take a look at one. Let's say Celsius and Fahrenheit, okay? That we want to talk about that as a linear relationship. So let's put points. It doesn't matter. We can put them in either arrangement. So we're going to work with a linear model here. Give me a couple of conversions that you know such and such Celsius is the same thing as such and such Fahrenheit.
0 degrees Celsius is 32 degrees Fahrenheit.
Okay. Everybody comfortable with that one? Right? Give me another one.
100 degrees Celsius is 212.
100 is
212.
212. Is that right? 212?
Mm-hmm.
We all right with that?
Yep.
So that's freezing point and the boiling point, right? You've got a linear relationship in this model between C and F. So typically, this would be an X value, right? And this would be a Y value. Don't we normally write Y in terms of X?
Mm-hmm.
So let's write a function for F in terms of C. Linear function. Okay, our slopes are usually found by difference of y's over difference of x's. But now we don't have y's and x's, we have, what are the y's? F's, second elements. And over the difference of the x's. In order, right? In the same order. So what do we have there? 180 over 100? Which is 18 over 10, which is 9 over 5. So there's our slope. And we can take our old friend here that we just used earlier. Probably we're all used to that one. Now let's just convert it to our C's and F's. So this is what? F minus F1 equals slope C minus C1. This is a general F, and this is a general C. This is a specific F. Which one of these do you want to? We can plug in one of these. It doesn't matter. Top one,
Zero.
a little bit
Zero.
easier.
Yeah.
So what's the specific F, 32, equals slope, 9/5, C minus the specific C value, and we get our function, right? Take the 32 to the other side. Everybody all right with that? Linear problem, linear model, but it's not some generic X and Y. It's a conversion table. If we know the Celsius temperature, we can multiply it by 9/5 and add 32, and we've got the Fahrenheit. Do that. What's the Fahrenheit equivalent of 37 degrees Celsius? Remember, one of my goals is for you to leave this class confident that you can do this stuff, so please do that. Doesn't do you any good that I can do it. Anybody got a calculator punching that thing out?
98.6.
Hey, how about that? What is it?
98.6.
98.6, right? Does that sound familiar?
Mm-hmm.
So there's normal human body temperature in Celsius, right? All right, so linear models we know a lot about, and that we can use them with X's and Y's, and we can adapt them for other letters and symbols if we have them, and we know, in fact, it's a linear model. Now, the next category is polynomials. We could probably spend the rest of our time there, because the nice thing about polynomials are they are smooth curves. They don't have any corners, cusps, no abrupt changes in direction. They always transition real nicely and smoothly from increasing to decreasing. So that's why, as cheesy as it might sound, polynomials are our friends. I mean, that's true, because we've got a whole bunch of other functions that give us all kinds of grief. Polynomials don't normally do that. So when we talk about polynomials, we're talking about things like this. And we want the exponents to be, you tell me, what kind of exponents? If it's a polynomial. Could I have an exponent of 2/3? No. Not if it's polynomial. So we want non-negative integers. Exponents are non-negative integers. So we can talk about x to the 11th, x to the 39th. Have all kind of coefficients you want to, real valued coefficients, but we don't want exponents like 2/3, -1/3, -1/2, because that makes graphs do crazy things. So these are smooth, and they are continuous, both of which are very nice when we're graphing and analyzing functions. So polynomials are nice to work with. We talked about these being used as mathematical models. Let's look at this. This particular function right here. So our points would be in this form, t comma s of t. And let me put some words to this equation. Remember, that's one of the ways we can take a look at a function, is verbally. Say that we're projecting an object upward from a height of 50 feet. There's its initial position. We're projecting it upward with an initial velocity of 48 feet per second. There's the initial velocity. Does this look familiar? Kind of a physics equation. And then this is the gravity part. If it's a free-falling object, that's the piece that we put in there that it's the only thing that is acting on that object after its release is that gravity is affecting it, right, at negative 32 feet per second. So there's the mathematical model. Could we, if that is in fact this neglects air resistance, by the way, if we're looking at that in a situation where it's neglecting air resistance, could we figure out what is the position of this object at time 0? How do we do that? Plug in t as 0. We want the s of 0, right? Now, does that correspond with what I said? Not that I'm going to tell you the truth all the time, but I'll tell you the truth most of the time. What is its position at time 0? 50. That was its initial position, right? It's 50 feet off the ground when it's projected upward. Okay, and then we could, well, what about this? How stupid is that? That's pretty stupid, isn't it? So what should we mention that makes this ridiculous? It's not part of the domain, is it? Because what is t? T is time, and unless we have our little, what is it, a flux capacitor handy from the movies, I don't think we're going to be able to find the s of -1. So our domain is that t is 0 or larger. That's the natural domain of this function. So that's ridiculous. If we wanted to see what the position is of this 5 seconds after it's projected upward, we would plug 5 into the function, do what it says to do, -16 times 5 squared plus 48 times 5 plus 50. I'm not trying to get a bunch of arithmeticians when we leave this class. That's why we have those little machines. As long as you know what to do with it, let the machine do the ugly part, and then we can figure out what is the s of 5, which is the height or position of this object after 5 seconds. So that is a quadratic polynomial, right? All the exponents are 2 or less in this case. Okay, working our way down, power functions. Power functions can really take on 2 looks depending on the nature of the power function. They could, in fact, be polynomials. So that could be a power function, or we could have a power function that not only in the form of the exponents being integers, but we could have the exponents in the form of 1 over an integer. And that still constitutes as a power function. That's not a polynomial because they behave very differently. So you could have another one and we'll still classify those as power functions, but they behave very differently from polynomials. Rational functions. Rational functions is a rational function is the quotient of some polynomial divided by another polynomial. The end result is not necessarily a polynomial. In fact, in most cases, it's not a polynomial. So the quotient of 2 polynomials, now we've already looked at one example today. That was a rational function. We looked at that. I think we started class with that today. Is this a polynomial? Yep. Not much of one, but it has all exponents that are non-negative integers. Same thing with this one. So the quotient of two polynomials is a rational function. The quotient of two polynomials in this case is clearly not a polynomial because we have some discontinuities, don't we? Where did we decide the discontinuities take place here? Have to take a little intermission, right? Where are the intermissions? 2 and negative 2. The graph, in fact, doesn't exist there. Does not exist at 2 and does not exist at negative 2. Algebraic functions. Algebraic functions, they can be kind of ugly. They can have corners. They can have cusps. They can have all kind of things that are, when we get to derivatives, they behave badly. Not as nice as polynomial functions. So we can have an algebraic function. Something like that. That's an algebraic function. Can have roots in it, can have addition, subtraction, multiplication, division, but it's not classified as anything else per se. So they behave badly. We'll find that out. Trigonometric functions. Some of you may be a little worried about that piece of this class. Maybe your advanced algebra and trig class in high school just didn't really dive into trig the way you would have liked to have done that. Maybe your Math 111, if you're coming out of Math 111 into this class here on this campus, if you ask my personal opinion, 111 probably needs a little extra dose of trig. So let me direct you that if you're a little bit hesitant or you're not feeling real good about the trig that's going to be in this course, I think it's, well, let me find out exactly where it is. There is a appendix C in the back of the book. If you're the least bit hesitant about what we're going to do with regard to trig, and I'm talking about the 6 basic trig functions, sine, cosine, tangent, and their reciprocal functions, anything hesitant on your part, dive into appendix C, and that will hopefully make our analyzation of trig a little bit smoother for you. Exponential functions. In fact, let's take these next two together. It's hard to separate them sometimes. Exponential and logarithmic. What relationship do they have? Besides that, gosh, that would have been nice if they were 6 and 7. I heard a stupid joke over the holidays. Why was 6 afraid of 7? Because 7, 8, 9. Isn't that stupid? Both of my children did the same thing you did. Like, get out of here, Dad. Do you understand that? 7 consumed 9, 7, 8, 9. So 6 is afraid of 7. Sorry. So 7 and 8 here, exponential functions and logarithmic functions. What are they? Aren't they related somehow? They are inverses, right? Does that ring a bell? Somebody, in fact, just rang a bell. I heard that. Was that a watch? So let's start off with an exponential function. Let's make it simple, kind of simple. The good old natural exponential function, y equals e to the x. We have an idea what that looks like. Does that look like y equal e to the x, asymptotic to the x-axis, increasing from left to right? Right, the range is positive. Domain is everything you want it to be. Suppose we want to find the inverse. How do you do that? That's a prerequisite to this course. Can you find the inverse of a function? Switch the x and y. So if we're going to interchange x and y, and now we're going to solve for y, well, That's going to be kind of a tough thing to do, isn't it? What is y? Y is up in the exponent position. So let's just describe what y is. Y is the power to which e is raised. What's a good old mathematical way of saying that? The power, the exponent, the log. Y is the log, y is the power, y is the exponent to which e is raised to get x. Does that look right? Now, it probably doesn't look right, does it? Let's adjust it a little bit because of the nature of this base. How do you normally see that statement? ln, right? So y is the natural log of x. That's when you talk about the natural log of something, you're talking about the power that you would raise e to get that thing. So it's easy to connect exponential functions and logarithmic functions. These two are inverses of each other. Now, if they are inverses of each other, shouldn't I be able to come in here and do a mirror image on either side of the line y equals x, right? So I can take this point 0, 1 and come over here and graph 1, 0. Is that okay? Shouldn't they appear as the mirror image of one another on either side of the line y equals x, right? Mm-hmm. So when you switch x and y, that's what happens. They are the mirror image of one another on either side of that line. Okay, and to finish this up today, transcendental functions. These are functions that are clearly not algebraic. Not algebraic. Now, a lot of these things that we've already talked about are, in fact, transcendental functions. Trigonometric functions are transcendental. Inverse trig, we haven't talked about that. Maybe we need to take a real quick look at an inverse trig problem. Exponential, that's transcendental. Logarithmic, that's transcendental. But clearly not algebraic. Let's look at an inverse trig problem to finish today. Do you have a preference in here? Is this the same as the Elmo, or do you have, this is called an Elmo, by the way. Is the Elmo easier for you or the board easier? Does it matter? Either way?
The board's kind of easy. It's got a glare on the screen.
Oh, you have a glare on the screen, so I better kind of do both. Okay, all right, I like that. Suggestions, you're thinking. And the answer is yes, I would mind. I'm not going to use it. Let's look at, I'll try it. It doesn't give me much room to get my big old body out of the way, but let's try it. Let's say that we want to, and I'll just pick a single value here just to get a quick look at an inverse tangent. So what are we really looking for when we're looking at an inverse tangent problem as opposed to a tangent problem? With a tangent problem, we plug in an angle, typically, push the tangent button, and it takes the tangent of that angle for us, and the result is the tangent of that angle. Now we have the tangent of the angle, we're looking for the angle, right? What angle has this for its tangent? Anybody think of that right off the top of your head? I think Appendix C might get a little attention between now and next class. It should. I mean, I don't think trig, I don't think we in Math 111 do it adequately, so I urge you to look at Appendix C. Anybody? What angle has 1 over the square root of 3? By the way, when in doubt in this course, let's use radians. So if you have a choice of degrees in radians, choose radians. Anybody?
30.
30? 30 degrees or pi over 6, right? So if we look at our good old friend here, a 30, 60, 90 triangle, where the side opposite 30 is half the hypotenuse. There's our old friend, right? That should be a friend. That better be a good friend. So if we start down here at 30 degrees, which is has the radian equivalent pi over 6, the tangent of 30 degrees ought to be opposite over adjacent, right? 1 over the square root of 3, and that's what we're talking about. What angle has 1 over the square root of 3 for its tangent? How is this? Is this thing in the way for some of you? I'm going to be running all over here trying to make sure everybody can see. Okay, I've picked out some problems. I think I gave you the problems from 1.1. Complete those if you haven't done so. And here's a shorter list from 1.2. I'll put those over here. And if you can have those prepared by the time we reconvene on Monday, it would be to your advantage and also to mine. So that'll finish us today.
What page are those on? What page?
Oh, I'm sorry. It's 1.2, pages 35 to 38.